All right, in this video we're going to talk about the equilibrium regarding compounds that are somewhat soluble or insoluble in water. We'll go over what can actually affect some of the solubility in a future video, but we'll just talk about basically the general form of solubility equilibrium and do some introductory problems with that, like comparing solubilities of certain substances, determining the solubility in terms of molarity or in terms of mass per unit volume. So yeah, I have some good news and I have some bad news regarding solubility. We'll start off with the good news. The good news is that if you can already do all of like the ice table and equilibrium math that we've been doing so far, if you're good at that, this is dead easy. But the bad news, and this isn't so much bad as in I may have possibly technically lied to you about something. So in a strictly technical sense, and as we know, technically correct is the best kind of correct, the solubility rules that we gave you are, strictly speaking, a lie. The reason why is because we don't say that things are entirely insoluble. What we say a substance is insoluble, what we actually mean is that it just isn't very soluble at all. So solubility is extremely low. I think the current guideline that they use for it is like 3 grams per 100 mils of water or something like that. Right, so things that just aren't very soluble, we call insoluble, even though to some degree it will actually dissolve into ions. All right, so solubility product, or KSP, so this is the equilibrium for dissolving. Right, so silver chloride dissolving will form the silver ion and the chloride ion. This dissolving process is not very favorable. If we look at the K value, you see how the K value is 10 to the minus 10th. A lot of KSPs will be extremely small, like 10 to the minus 10th is actually reasonable compared to a lot of them. Some salts we'll work with may have K values like 10 to the minus 50th. Right, so our equilibrium expression is silver ion times chloride ion. Again, no denominator because AgCl is a solid, and that makes it not included in the equilibrium expression. And I actually gave you the value here for KSP of silver chloride because we're going to use it in a couple of minutes, right? So now one thing to keep in mind is you can't just compare KSPs to determine if something is more soluble. There's an extra step you have to add in. Right, so these are common KSP patterns that you'll see when you start plugging these things in to determine solubility. If your ion's a 1-to-1 ratio, like for example AgCl, then when you start doing your ice table, you will wind up with x times x, or x squared. If it's a 1-to-2 ratio, you'll wind up with x times 2x quantity squared, or 4x cubed. 1-to-3, again, we're going to have x, 3x quantity cubed, and a 2-to-3 ratio will be 2x quantity squared, 3x quantity cubed. Right, so these are some general patterns that you'll see to help you kind of speed up your equilibrium math a little bit for solubility. If you want to memorize these, go ahead. You don't have to. You can just, again, go through and figure them out manually, but they'll just keep repeating over and over and over again. All right, so again, so here's our first type of basic problem. We want to know how soluble a substance is. All right, so we want to know how soluble, so molar solubility, so we're talking about moles per liter or molarity of AgCl given this. Right, so we'll write out our expression. So AgCl solid gives Ag plus Cl minus. And again, to show you why this works, this is going to be like a minus x here, so we're going to have plus x. Right, so we're going to say that KSP is equal to Ag plus Cl minus. Plug in all of our numbers. So we're going to say that 1.8 times 10 to the minus 10th is equal to, this is going to be x times x, or x squared. So X, which is going to be our molar solubility in this case, we'll just square root, and we'll wind up with 1.3 times 10 minus 5 molar. Right, so silver chloride will be soluble to the extent of 1.3 times 10 to the minus 5th molar, or 13 micromolar. Right, not a lot. So you'll be asked for, in this case, I asked for molar solubility. If I asked for example, let's say like grams per liter, this is an easy conversion, right? If I wanted to know how many grams I could dissolve in a liter, well, I have 1.3 times 10 to the minus 5 moles per liter times, I just do a mole conversion, right? 1 mole of AgCl is going to be 143.32 grams. I plug this in, and I get 1.9 times 10 to the minus 3 grams per liter. Right, so roughly 2 milligrams of silver chloride will dissolve in a liter of water. Not very soluble at all. So you can kind of see why we say it's an insoluble salt. Right, so this is working from KSP to molar solubility or mass solubility. You could be asked to reverse this process, right? I could give you the solubility in terms of molarity or in terms of grams per liter or something, and ask you to work back from here to the KSP. Same deal, right? You just reverse the math. Now we can actually make it a little bit more complex, but not much. Right, so we'll try to compare some solubilities here. So AgCl versus CaF2, and I gave you the two KSP values. Now the trick here is you can't just compare the values of KSP to figure out which one is more soluble. Right, so if we look at these 1.8 times 10 to the minus 10th and 3.4 times 10 to the minus 11th, it would seem that AgCl is more soluble. I'll tell you right now it's actually less soluble. The reason why is because of the difference in equilibrium expression. Right, so we'll just do out that problem, same thing. So AgCl. Now we already know that, right, so KSP was Ag plus Cl minus, which was x squared. Right, and we got our value of x previously, so we already did this one as 1.3 times 10 to the minus 5th molar. Now if we look at CaF2, for CaF2, we're going to have KSP equal to concentration of calcium ions, concentration of fluoride ions squared. So 1 to 2 ratio means I'm going to be working with a 4x cubed expression, right? Because x and then 2x squared. So what we're going to have here is we're going to have 3.4 times 10 to the minus 11th equals 4x cubed. X is going to be equal to 2.0 times 10 to the minus 4th molar. So notice, Ks, or in this case, calcium fluoride, is more soluble even though it has a smaller KSP value. The only time you can directly compare KSP values is if they have the same pattern. Right? So if you have two salts that both use the x squared pattern, then just KSP value will tell you right away. Or again, if you have two salts that are both 4x cubed, KSP will tell you right away. But if you're comparing salts that use different patterns, actually do out the math.